is really a classic problem. This is acceleration due to gravity on Earth. So this one I think is a little easier to kind of picture in your head what's happening. This is if you're in a vacuum on Earth, acceleration due to gravity is constant, right? You may have heard that before, and we measure distances in two ways, really. Meters, which is a better way to do it. So the acceleration constant is 9.8 meters per second squared. As if I drop an object and there's no air resistance, it's going to fall. And I like to put a negative in front of that because that indicates direction. Right, that's going down. It's going to fall down at 9.8 meters per second squared, which is equivalent to 32 feet per second squared. Okay, so we'll see where these numbers kind of pop up when we jump into this. So right now our position function in acceleration due to gravity would be, if it's in feet, it's negative 16 t squared plus initial velocity times t plus the initial position. Okay, and if it's meters, then it's negative 4.9 t squared plus initial velocity times t plus s naught. Okay, so this is our first example. So that means I could pick out, if I wanted to, that it's thrown upward at 64 feet per second, and it's thrown off a height or a building of 96 feet high. Okay, so what's going on here? So you could, if you wanted, before we jumped into the calculus part, you can see that this one they would graph like this. This is 96 feet, and then we could find the vertex if we wanted to, but it should go up as velocity is positive. So that sends it in the positive direction, and then it should fall, and it should hit the ground. Okay, or the river in this case. All right, now be careful because this isn't the path of the object. I guess kind of like the first example, the object is just going up and down. So really it just goes up and then it goes down. Goes up, stops, and goes down. So just like the horizontal. So you got to be careful. It wasn't thrown. That's a different calculus problem or a physics problem. It wasn't like thrown at an angle. So it up and went down, but its position, its height, up and down would be given, just like the last problem, by inputting the time to find the height, or s. Okay? So, for example, like, where is, if you wanted, before we do the calculus, where is it after 1 second? Well, let's see. Negative 16 times 1 plus 64 plus 96. What does that give me? That should be 86 feet. Okay, so that means if it started, interesting. So if it started here at 96 feet and it got thrown up, then it probably got above 96, but then after a second, this thing's moving quick, it went back down and got below. So I would guess if we looked at it like 0.25 seconds, it's probably greater than 96. All right, let's take a look at the calculus piece to this. Velocity. So we know the velocity function is the derivative of the position function, which should give me that. Okay, so acceleration then would be the position of this. Oh, this is interesting. Now you can believe me, the relationship between position, velocity, and acceleration, and we see that this is indeed a constant. Acceleration due to gravity on Earth in a vacuum is 32 feet per second squared. Okay, and the same thing would work if we did the meters version of this guy. Okay, what is the highest point above the river reached by the stone? Oh, interesting. Now we had an algebra way to do this. This is called a vertex, right? So we could find out the time. Oh, this is good. The time and then the height. And you might remember that there's this little formula, negative b over 2a. That gives you the input for the vertex, and then you can plug that in and give you the output. This was the algebra way. But now we have a more clever way to do it. When does the object reach the max height? The max height when the velocity is 0, right? Because if your object is traveling straight up, then it's going to stop here and then be pulled back down by gravity. So this, what happens here at the height, this would be when the velocity is 0. Ooh, that's good. So let's do it. Negative 32t plus 64 equals 0. And I can solve this pretty quickly to determine that it'll take 2 seconds to reach the max height. Okay, that's not the answer, but that's how long it took to reach the max height. Okay, let's see. Why does that not make sense with this problem? I think I must have made a mistake, because after if it takes 2 seconds to reach its max height, then after 1 second we should be higher up. I think I made an error with my calculation here. Let's try that again. 16 plus 64 minus 16 is, what is that? 48? Yeah, so this should be much higher. I got an error here. You might have noticed that before. Let's try that again. 16, I'll use my calculator this time. 16 negative plus 64 plus 96. There we go, 144. So it goes up, and then it keeps going up, and then it falls down. Let's see how high it goes. We know that it reaches a max after 2 seconds, but the question is, what's the max? So, what function do we plug it into? Don't plug it into the derivative. We use the derivative to get the information, but now we're going to plug it in to our position function because it asks what's the highest point. Okay, so we got to plug that back into our original function, which is 1664.96. And that should be equal to 96 feet. Okay, so think about that. How do we find the maximum? This is a big topic in calculus. We're going to do this a lot in the future in this course. How do you find a maximum? You take the derivative, set it to 0, and then there's something happening there. When we get to more complicated functions, this is either a max or min. Derivative 0, horizontal tangent, tangent line 0, derivative 0, derivative 0. So it's either a max or min. When I set my derivative to 0 and solve, it's either a max or min. We know this one's a max because the function is quadratic and it goes with a negative coefficient leading, so it goes up and then down. We only have a maximum. Okay, with what velocity will the stone strike the river? Oh, good question. So when it comes back down, what's the velocity? So that means, how do I answer that question? I got to plug in some time value into my velocity function, but what's the time value? So we have to know when it hits the ground. So we got to go back to algebra. Negative 16t squared plus 64t plus 96. Okay, so again, in this class we go back and forth from calculus to algebra, or from our function given to our derivative function. There's a relationship, right? If we want to know how fast it's going, or velocity, when it hits, we first need to know when it hits. And to solve the question when it hits, we need to solve this equation. All right, so do you remember your factoring? I'm going to factor out a negative 16 because it goes into all these numbers, I think. That's t squared minus 4t. And is that going to be, what is that, 6, right? Yeah, minus 6 if I did that right. And then t and t, and I'm trying to factor that thing if it factors. But bad news, it does not factor, so we're going to have to use the quadratic formula to solve this, because I can't find two numbers that multiply together to give me 6. 6 would be like 3 and 2, and there's no way I'm getting a 4 out of here. Okay? But the good news is I can do a little bit, save myself a little bit of trouble with that quadratic formula by using these numbers, right? Because if this thing's 0, 0 times negative 16 is 0. Okay? So real quick review of quadratic formula. We're going to say t equals negative b plus or minus square root of b squared minus 4 times a times c all over 2 times a. Okay, and if I'll skip the work for that, that should be about, you get two solutions for that, right? Because it's quadratic. You plug that into your calculator, you get these two guys. Get rid of that one because our model only starts for positive values. And then finally, I can answer the question, the velocity when it hits the ground, which takes 5.16 seconds, is, I plug that into my velocity function, which is negative 32 times 5.16 plus 64, and that should give me negative 101.12, and we got to use our units, feet per second.